Hello everyone, my name is Jordan Glass and this is Lab 2, Lines of Charge. So the purpose of this lab was to use a more accurate model to find the value for the charge on one piece of tape. And using the experimental data we found in Lab 1, we used GlowScript to model the tape as a line of point charges rather than one single point charge. We sought to determine the extent to which the charge value of the top tape differs between using the two models. And starting initially with the charge of the upper tape we found from Lab 1, we kept changing this Q value and running the model until we found a charge value that made Fe equals Fg. Ultimately, we found that the charge of the top tape is larger than the value we calculated in Lab 1. So the models we used in this lab are basically that many objects in real life cannot be accurately represented as a single point charge. Rather, they're more accurately modeled as a distribution of point charges along the length, area, or volume of an object, especially when the two objects are close to each other. This can be done by finding the magnitude of the electric field produced by a very small portion of the bottom tape on some very small portion of the top tape, then repeating this procedure many times across the length of the tapes, and then ultimately summing these electric fields to get the net electric field. The system in this lab was the upper tape, while the surroundings can be considered as the bottom tape and the earth. Some assumptions made were that aside from the force due to the electric field and the force due to gravity, all other forces, including air resistance, were negligible. We assumed the charge was perfectly evenly distributed along each of the tapes. So there was no new experiments done in this lab, but we did use some experimental data from Lab 1 in the GlowScript model, which was the mass of the tape and the distance between the tapes and also the charge of the upper tape. So the first part of the coding was to basically add the E-field function from lab 0 to help calculate the dE, which this function would be used later on to calculate the each dE. We also added the mass and charge we found in lab 1 as well as some other constants. So then moving on, next this is pretty much just a starter code that we use to create the actual lines of charge. And we were given freedom to choose how many charges we wanted to have, and I chose 50. As the larger the number, the more accurate the model will be. And we also inputted the distance, as you can see right here, the start pause, to accurately reflect the distance we found in Lab 1 between both the tapes. So then we began calculating the electric fields and net electric force from each DQ from the bottom tape to each point on the top tape. We also made an arrow representing the net electric field on the top tape and adjusted its scale factor to make it easier to understand and visualize. As you can see right here, scale is very small for the electric field arrows, and then for the force arrows and also the FG arrows, it's quite big. So then we made the arrows that represent the electric force and gravitational force, and as I said, they use the same scale and they're equal and opposite um, after we found the right Q, which after finding that Q value that made them equal, we found it was 2.16 times 10 to the negative 8. So what if you'd model each of your tapes as a single point charge like in the previous lab? So we did do that in the previous lab, and we found that it was 9.1 times 10 to the negative 9. And when modeled as a line of distributed charges, the charge value was 2.16 times 10 to the negative 8, which is over double the amount of the point charge model. And why do these estimates differ? Which value is more likely to be closer to the real value, and why? So basically, when modeled as a line of charges, the value differs because you take into account the nuance that there are multiple infinitesimally small charges at play that each contribute a small electric field towards the top tape, resulting in a sum that is bigger than if you modeled it with a single point charge in one fixed location. While the magnitude of the electric field from one of these small DQs to some small point on the top tape would be smaller, but if you add them up across the length of the tape, the net electric field becomes greater than the point charge model. And yeah, the line charge model is more accurate to real life because tape is two-dimensional and the charge is evenly distributed along it. So the conclusions we made was that the charge on one piece of tape is more likely 2.16 times 10 to the negative 8 as predicted by the line charge model. And while using the point charge model, it resulted in a charge of 9.1 times 10 to the 9. And the line charge model is more accurate as the tapes in the experiment have charge distributed across the entire length. The charge is not concentrated at one central point along the tape. So yeah, that's it. Thank you for watching.